Physical Science Exam 2015, question 17. The table of relative atomic masses included on the information sheet is based on carbon 12 equal to 12.00. So if we have a look in here, what that means is we can have a look at the periodic table of elements and we have a look at carbon, and this one's 12.01. It's a bit odd what's going on there. They're based on the fact that carbon 12 is 12 point, that's the relative atomic mass. So what does this actually mean? Explain what this means. It means that the masses of all the other atoms are compared on a mass scale where carbon 12 is equal to 12.00. So that's what we're going to have here. So the masses of all atoms are rated such that carbon 12, i.e. the isotope of carbon that has 6 protons and 6 neutrons, is equal to 12.00. Good. Okay. What have we got here in part 2? The table of relative atomic masses shows that there are virtually no elements whose relative atomic mass is a whole number. Explain why this is the case. I mean, you would expect to find with an element it has a certain number of protons and a certain number of neutrons, and when you consider those, the atomic mass will be a whole number. It should be an integer. But in all of these cases, or the vast majority of these cases, you see that these are not. Such that magnesium is 24.31, we have boron here, which is 10.81, and so on. What's going on there? So since elements exist in isotopic forms, such as carbon, for instance, that's an example, we have carbon 12, carbon 13, carbon 14, they're examples of those, and they have a relative abundance, then what this means is that we are going to find the percentage of, well, we have the percentage of these isotopes as they occur in nature or in any block of that particular element, so they're going to have different masses, and so the weighted average of those masses is going to give you a number that is not a whole number. So elements exist in isotopic forms, and the relative abundance of these isotopes give a non-integer result. Okay, so the mass spectrum below shows the relative abundances of the 3 isotopes of a naturally occurring element. So we have here relative abundant isotopic mass here, 86, we have 10% of that, 87, we have 7% of that, and 88, we have 83% of that. From the data shown in the graph, calculate the relative atomic mass of the element. So the atomic mass of X is going to be equal to the percentage multiplied by the relative atomic mass of each of the isotopes, added those up, and then divided by 100. So what we have here is 10 multiplied by 86, which we get from here and here, plus 7 multiplied by 87, which we get from there and there, plus 88, or 83% times 88 for the relative isotopic mass, there and there, and we're all going to divide that by 100. I'll get out my trusty calculator. What we have here is see if I fit that so you can actually see it. Turn that on, is that going to make things better? Try that. So we have 10 times 86 plus 7 times 87. Oh, delete that one. Don't need that there. Delete that. Plus 83 times 88 equals that. Divide that by 100. And we get the total is going to be equal to 87.73. And put that down. And finally, hence or otherwise, use your information sheet to identify the element. Well, we know that the relative atomic mass is 87.73. So if we bring this back and look here and here at our relative atomic masses, we've got 85.47 for rubidium. Yttrium has got 88.91, but right in the middle of that, we've got strontium, which is the closest with 87.62. Strontium has an AR of, what did we say it was? 87.62. Close enough. And that's the end of question 17.